knows a lot about the science stuff. Professor Dave explains.
In an earlier tutorial, we briefly discussed the difficulty of hydrogenating alkenes. Although exergonic in most cases, and therefore thermodynamically favorable, it remains problematic from the standpoint of kinetics, such that hydrogen gas and an olefin will essentially never react on their own, requiring some kind of catalysis. For some time, this has been and still is a fascinating topic of research, as demonstrated by the number of Nobel Prizes awarded to hydrogenation chemists. As we also mentioned previously, an early solution to this kinetic problem was found in 1897 by French chemist Paul Sabatier, who discovered that gaseous mixtures of ethylene and hydrogen could be converted to ethane by action of a nickel surface under extreme conditions. For this process, Sabatier received the 1912 Nobel Prize in Chemistry. Nickel is still used, industrially as well as in the laboratory, to hydrogenate alkenes. Chemists now use a special grade of finely divided material called Rainey nickel in honor of its inventor, American engineer Murray Rainey. Supported palladium is widely used as well, often as palladium on charcoal. Rhodium and platinum are other surfaces commonly used to hydrogenate alkenes. Industrially, these processes are important in the petroleum industry, as alkanes are better and cleaner fuels than unsaturated hydrocarbons. The same goes for the food industry, where unsaturated vegetable fats are often hydrogenated to yield more saturated products, like the well-known margarine. From a stability standpoint, saturated hydrocarbons are preferred products because they do not easily react with oxygen, forming unstable and toxic hydroperoxides. The mechanism of these hydrogenations is understood in its gross features as shown in the following scheme. In the solution or gas phase, both the alkene and the hydrogen molecules independently diffuse towards the active metal surface. The olefin is chemically adsorbed onto the surface, forming a loose pi bond with the metal, whereas the hydrogen molecule is reversibly cleaved to form two MH bonds. If the alkene is bound at the site vicinal to a newly formed MH bond, a metal alkyl complex is formed as the hydrogen is transferred to one of the carbon atoms in the olefin. This step is reversible. We know this because with incomplete reactions, we observe alkene cis-trans isomerization, which means the metal alkyl moiety has time to rotate around the CC bond and redeposit the beta hydrogen onto the surface. For the final step, the atomic hydrogen must migrate next to the metal center bound to the alkyl for the reductive elimination to take place, thus releasing the alkane product. This is the energetically favorable step of the catalytic cycle, and it is irreversible. Alkynes are hydrogenated to alkanes by a double hydrogenation mechanism similar to the one we just described. However, the first step is usually faster than the second one, and it is possible under select conditions to stop at the alkene stage. Alkynes are hydrogenated to alkenes most commonly using Lindlar's catalyst, which is a special grade of palladium metal supported on barium sulfate and poisoned with quinoline. This reaction, which occurs with stereoselectivity for the Z-alkene, should be familiar from our study of organic chemistry. Industrial hydrogenations are complex to develop due to the gradual fouling of the catalytic surface, with increasing deposits of carbonaceous material altering the rate and selectivity of the reaction. For simple industrial substrates like petrochemicals or fatty acids, these difficulties are tolerated. For more value-added products, such as fine chemicals and pharmaceuticals, a milder and more selective form of hydrogenation is used, such as homogeneous hydrogenation. The catalysts are usually rhodium, iridium, or ruthenium complexes, which are quite soluble in organic solvents. They work by a qualitatively similar mechanism as the one we just discussed for heterogeneous hydrogenation, with a few added complications. First, the metal is coordinated to a number of ligands, and ligand dissociation acquires a special importance. Second, we have seen that alkenes and hydrogen diffuse and react with a metal surface independently. In homogeneous catalysis, the order is important. There are hydrogen-first catalysts and olefin-first catalysts. Out-of-sequence coordination usually inhibits catalysis. The prototypical hydrogen-first catalyst is Wilkinson's catalyst, developed by English chemist Geoffrey Wilkinson and acknowledged with the Nobel Prize for Chemistry in 1973. This rhodium catalyst reacts under extremely mild conditions, often room temperature and atmospheric pressure of hydrogen gas, and displays excellent chemoselectivity. If a polyunsaturated substrate is present, the chances are excellent that the less substituted double bonds will be selectively saturated. This means that mono and di-substituted olefins can easily be hydrogenated, but the more substituted substrates do not react readily and are left untouched. There is only one puzzling feature to this selectivity trend, and that is the position of ethylene, the least substituted olefin, and yet the most difficult to hydrogenate. How could this be the case? To answer this question, we need to look at the mechanism. First of all, let us look at the structure of the catalyst. It is a rhodium-1 species, so it is a D8 species. 4 2-electron donors make Wilkinson's catalyst a 16-electron species. We have seen that many compounds of rhodium-1, iridium-1, palladium-2, and platinum-2, all 16-electron species, are very stable in a square planar geometry, so a bit counterintuitively, binding of a fifth ligand to reach the usual 18-electron quota is not favorable. The reason for this is the high potential energy of the B1G orbital, which makes bonding at the two axial positions thermodynamically labile. As a result, in many catalytic cycles, the intermediates are 14-electron species, which means the reaction is L-dissociative. This is the case with our rhodium catalyst, and hydrogenations are inhibited by added triphenylphosphine. We consider the empty coordinating position loosely occupied by the solvent if the solvent has any donicity. For the electron count, however, we consider this position empty, given that solvents like dichloromethane, benzene, or methanol are poorly coordinating toward rhodium, so consider this just a formality. Let us follow the rest of the mechanism. The first species in the cycle is I1, which is electron poor with 14 electrons, and therefore eager to acquire ligands. Oxidative addition with hydrogen gives I2, now a 16-electron species, and also featuring a higher oxidation state than before, rhodium-3. At this point, the alkene coordinates through its pi cloud to yield I3. Hydrometallation follows, with the syn H migrating to one of the carbons in the alkene. Now I4 needs to isomerize to yield I5 for the reductive elimination to take place. The hydrogen and carbon involved in the reaction need to be close to each other, so the reaction cannot occur in I4 because the two substituents are trans. There are several mechanisms for isomerization at the rhodium-3 center, but it is a bit too complex to discuss them here. We must simply know that isomerizations in these species are quite easy to achieve, and so I5 is formed readily at equilibrium. Reductive elimination can thus generate the alkane product and I1, which initiates the cycle again. Most of these steps are reversible, and there are other intermediates in the scheme which we have left out for simplicity, but what we have highlighted is the basic mechanism for a number of hydrogen-first transition metal catalysts. With the mechanism now understood, we can explain why ethylene does not readily get hydrogenated. Species I1 reacts almost irreversibly with ethylene to form the off-cycle species OC1. This is not an intermediate in the hydrogenation, as it does not react with hydrogen gas, and therefore ethylene acts as a poison, permanently occupying this coordination site and rendering the catalytic complex inactive. More substituted alkenes bind poorly and reversibly to I1, so their inhibitory effect is therefore small or non-existent. Thus, the catalytic cycle may occur as intended. Now that we understand hydrogen-first catalysts, how do olefin-first catalysts work? The basic steps are the same as what we just learned, but they occur in a different order. If the catalyst is an MH species, the hydrometallation can occur before the oxidative addition of H2, which occurs later, right before the reductive elimination. This is exemplified by the hydrogenation catalyst with the following formula, consisting of a rhodium center, 1 carbonyl ligand, 3 triphenylphosphines, which we can represent as L for ligand, and a hydrogen. First, one of the triphenylphosphines will dissociate to yield this square planar complex. If the catalyst then coordinates with an alkene moiety, in this case one that is monosubstituted, this is not a dead-end species like it was in the previous cycle we examined, but instead can insert via the pre-existing rhodium-hydrogen bond. It is at this point that oxidative addition of hydrogen will occur, pushing the carbonyl ligand down. And lastly, reductive elimination can occur with the newly saturated alkyl fragment and one of these hydrogens to yield the alkane product and regenerate the square planar 16-electron catalytic intermediate, thus perpetuating the cycle. So the interesting thing about this mechanism is that the hydrogen involved in the hydrometallation was already present on the catalyst, and molecular hydrogen will oxidatively add after this step to replenish this hydrogen and also perform the final reductive elimination. Many additional hydrogenation catalysts can be described qualitatively by one of these two cycles we just discussed, whether hydrogen first or olefin first. To summarize, we have seen how industrial applications of heterogeneous hydrogenation are carried out under harsh biphasic conditions. For more complex multifunctional molecules, like pharmaceuticals, chemists prefer homogeneous catalysts. We have seen that the success of these catalysts rests on the ability of the metal to easily switch between two alternating oxidation states, to coordinate reactants in a specific order, and to be able to associate and dissociate spectator ligands like triphenylphosphine when needed, to make room in the coordination sphere for the reactants. It is therefore evident that creating a truly effective catalyst is not an easy task and requires much empirical and theoretical work, especially because metals like palladium, platinum, rhodium, and iridium are extremely rare and expensive, and the requirement is for these catalysts to be robust and have a high turnover number. Alkene hydrogenation is still one of the most important areas of catalysis research, so we will continue to discuss this topic in the next tutorial, which introduces an aspect of stereochemistry.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.